Now, where you set this alpha level and how you interpret this p-value is essentially based on how willing you are to make an incorrect inference, because think about it. Say that we have a p-value of 0.02. Okay. Now again, what that means is if the null is true, the probability of finding the result we did is only 0.02. We're going to say, no, that's too unlikely. We don't think the null is true, and we're going to support our research hypothesis. Well, now think about it. Even if the null really is true, we're still going to find the data that we found some of the time. Sure, it's very, very unlikely, but it could happen by chance. Now, that means that if we're rejecting that null hypothesis, we could end up being wrong. So our p-value, and in particular any p-value less than our value of alpha, is also going to indicate the probability that we're incorrectly rejecting that null hypothesis. And that leads to the next point, that we need to realize that whenever we're doing hypothesis testing, just like we can never prove something right or wrong, we can never be sure whether or not we've drawn the right conclusion based off of our data. One way to think about it is in this sort of 2x2 contingency table, and Jackson sets up something similar that you can refer to in Chapter 7 as well. So, on the left, what this shows is whether or not we're going to make a decision to reject our null hypothesis or retain the null hypothesis, okay, or fail to reject it, that is. Okay? So we're always going to make one of those two decisions whenever we do statistical hypothesis testing. We're going to collect some data and we're going to make our claim. Either we reject the null and support our research hypothesis, or we're going to retain the null or fail to reject it. Now that's the type of decision that we're going to make, and in fact the true state of the world, which we may never know, and in fact do never know in behavioral science, is whether or not the null hypothesis is in fact really true or whether or not it is false. Now the reason I say that we can never know this is we may never know whether or not males are better or worse than females at some specific task, or whether or not some specific drug, if you give it to everybody, it's going to cure some sort of disease or become beneficial. Whether or not some method that people are using is going to work. Whether or not some sort of cognitive task results in better or worse performance. Okay, we never know whether these things are really going to be true for every single individual in the entire population. Okay, so we'll never know the true state of the world, but what we can do is talk about things probabilistically. Okay, so what do I mean by that? Well, there's really then four possible outcomes that can exist. Either we've rejected the null or we've retained it. That's the decision that we've made based off of our data. And in reality, that same null hypothesis was really either true or is false. Now, if we reject the null hypothesis and it's in fact false, that's sort of a best case scenario for us. Okay, we want to reject the null hypothesis because we're truly interested, remember, in our research hypothesis. And we're making then a correct decision if we reject it when it's really false. Similarly, even if we fail to reject the null hypothesis, okay, now that's not what we wanted to do, okay, that's not really the goal of our research because we want to reject that null hypothesis and support our own research claim. Okay, but we would still rather make a correct decision than a wrong decision, so if we end up retaining the null hypothesis or failing to reject it, and it's really true, we've still made a correct decision in that situation. Well, that means that there's two different types of errors that we can make. If we reject the null hypothesis, when it was in fact really true, that's what we call a type 1 error. Now the other type of error that we can make, a type 2 error, creatively enough, is if we retain the null hypothesis when it was really false. So we failed to reject it, but we should have. It was really false. Now, these are the two different types of errors that we can make. And what I mentioned on the previous slide is we set our alpha specifically to correspond to this type 1 error rate. Now, what that means is, if you think about it, like I just said on the previous slide, if we reject the null hypothesis, but it's really true, we've made a mistake. Now, if we set our alpha at, say, 0.05, that means that if we find something that we think occurs 5% of the time or less, we're going to call that too unlikely and reject the null hypothesis. Well, again, this is all probabilistic that we're talking about here. So, in fact, even if the null really is true, that same result that I'm talking about will still occur this 5% of the time. And that's why this alpha level corresponds to this type 1 error rate. That is the probability of rejecting the null hypothesis when it is in fact true. Now we can apply our probability concepts to then realize that if we're either going to reject the null hypothesis or retain it, we're going to make one of those two decisions. Well, then if the null really is true, and the probability of rejecting the null when it's in fact true is alpha, then the remaining or complementary probability, 1 minus alpha, is associated with the correct decision shown here in this upper left cell of the table. Okay? And just to establish a little bit of abbreviation or nomenclature that we're going to use later, a type 2 error then is referred to as beta in a probability sense. And the correct decision then in this bottom right cell is referred to as 1 minus beta. Okay, these are just some things you're going to want to jot down, and we're going to refer to these later. Now maybe this will all make a little bit more sense if we think about a concrete example. Okay, now this is going to be a toy example, and what we're actually going to find out about is how to start doing hypothesis testing based off of the observational frequency or counting data that you guys are going to be generating in your own research projects. But for now, let's think of just the most basic example to illustrate the points that we've talked about here in this lecture. So assume that you're going to toss a fair coin. Okay, and there's a lot of situations where you might really want to toss a fair coin and where you really want to be sure that it is in fact a fair coin. But let's assume you're going to toss a fair coin 10 times. Okay, now again, this is a coin that has heads on one side, tails on the other side. And if it's a fair coin, that means there's a 50-50 chance that it's going to land on heads or tails, right? Well, how many heads would you expect to find if you toss a fair coin 10 times? Okay, on average, how many times do you think heads is going to come up when you toss a fair coin 10 times? 5 times, right? Because the probability of landing on heads or tails in a fair coin is 1/2 or 0.5. Well, then if you toss it 10 times, then the probability of getting 5 of those as being heads is going to be 5 out of 10. And that's something you guys should be able to prove to yourself by now, knowing what you know about probability. Okay, and thinking about ands and ors and some of these things in different events. Okay, we're not going to prove that here. I'm going to hope you guys take my word for it. Well, what we can actually do, knowing the laws of probability, we can actually compute what is the probability of getting each number of heads if we toss a fair coin 10 times. And that's what's illustrated in the graph here. So what we have on the y-axis is the corresponding probability, and on the x-axis is the number of times we expect heads to come up in tossing a fair coin 10 times. And as you can see, the largest number, the mean, as well as the median and mode here, is 5. Okay, what we would expect most of the time, and on average, the mode and the mean, okay, is for 5 heads to come up when we toss a fair coin 10 times. But you can see the probability of that. In fact, every time you toss a fair coin 10 times, and you feel free to bust out a quarter and prove this to yourself, okay, is 1 in 4 times, that is a probability of 0.25, you're going to get 5 heads when you toss it 10 times. But you're not going to get 5 heads every single time you toss it 10 times. Sometimes you'll get 4 or 6. Sometimes you might even get 3 or 7. And as you can see here, sometimes you're even going to get heads 9 out of 10 times. It's not going to happen very often, because you can see the very low probability associated with a value of 9 heads over there on the right. But it is still going to happen sometimes, even if it is truly a fair coin. But this introduces the notion of hypothesis testing. What if our hypothesis was that somebody was flipping a loaded coin, okay, or a trick coin or whatever it is? Okay, say that you and your roommate are flipping a coin about whose turn it is to do the dishes. Okay, well, if your roommate's always flipping the coin and it's always coming up on heads, okay, comes on heads 9 out of 10 times, you're starting to feel a little bit cheated. So if you want to test that hypothesis formally, if you want to say, wait a minute, I'm not sure this is a fair coin that we're dealing with here, okay, then you can apply the types of concepts we've been talking about here. Okay, at what point, in fact, would you question whether the coin is fair? If heads comes up 6 times, is that unlikely? What if it comes up 7 times? What about 0 times? Okay, so how likely is unlikely, in fact? Okay, in fact, how unlikely is it to come up 10 times out of 10? Well, what we can do is to look at the probability of that. We know that the probability is 0.001 of getting 10 heads in a row when flipping a fair coin. We also know that the probability of getting 9 out of 10 heads is only 0.01 when flipping a fair coin. Well, these probabilities are exactly the p-values that we were talking about before. So say you have your roommate's coin. Your research hypothesis is that this is an unfair coin. Okay? In other words, that you think that it's not going to, that the probability of getting a heads is not 50-50 with this coin. So you flip the coin 10 times. Well, now what do you expect to find if the null hypothesis is true? Well, if the null hypothesis is true, this is a fair coin. And so you're going to expect to find 5 heads coming up. Now, as I just said, you're not going to get 5 heads every time you toss a fair coin. Sometimes you'll get 4, sometimes you'll get 6. So what we want to see is, okay, well, what's the probability of getting a specific result? So if flipping your roommate's coin ended up in heads 9 times, the probability of that happening, if it's a fair coin, that is the probability of 9 heads given the fair coin, or given the null hypothesis, is 0.01. That is, there is a p-value associated with the data that you have, these 9 out of 10 heads, of p equals 0.01. Well, if you in fact set your alpha level at 0.05, that is, if you say that I think that something happening with less than a 5% chance is too unlikely, and anything that occurs that infrequently, I'm going to say, I doubt this is a fair coin. It's probably a trick or a loaded coin. Then you can see that there's actually going to be quite a few outcomes here on this graph. Okay? Anything less than 3 or greater than 7 is going to lead you to reject the null hypothesis of a fair coin and claim that in fact you have a loaded coin here. So that is the end of it in terms of introducing these basic notions of probability as well as hypothesis testing within a specific example here. Now again, all we're going to be doing is looking at different situations where we apply this exact same notion. Thinking about if our null hypothesis is true, okay, if we're wrong in a sense, what does the distribution look like? What do we expect to find? With the fair coin example, the distribution is shown right here. And then we set some sort of criterion for saying, okay, what I'm going to say is, I don't expect to necessarily find the thing right in the middle, that is, the 5 heads, every single time here. What I'm going to do is to set some sort of cutoff of what I'm going to call too unlikely. And if I find something that is that too unlikely, then I'm going to reject my null hypothesis and accept my research or alternative hypothesis. In this case, if we set our cutoff at 0.05, then you can see any of the values that are produced with probability less than that 0.05, we're going to reject and say this must not be a fair coin. Because flipping it 10 times, I think 9 heads is too unlikely. I think 0 heads is too unlikely, and so forth and so on. And again, all that's going to change over the course of the semester and next is looking at the types of situations. Are we looking at counting data, such as your observational studies going to be? Are we looking at group comparisons? Are we comparing 2 groups or 3 groups, so forth and so on? So the situation is going to change, but this basic logic of hypothesis testing will remain the same. So it's important you guys understand this now based off of this lecture and the material in Chapter 7, and please ask questions in class if there's something that's still not clear. You should now be ready to take the quiz that's associated with this lecture. Quiz number 9 that can be found on Unica site. Please remember to do this. It's going to close 15 minutes before the start of class on Tuesday.